and we have been talking about premixed flames all along. Perhaps I should just make a general comment that the idea was that the fuel and oxidizer are completely mixed at the molecular level. So in the continuum approach that we are taking, when you look or you focus on a small fluid parcel, which mathematically is described by a point that contain, of course, many molecules, there is fuel and oxidizer mixed at that point, okay? The topic today is on diffusion flame, so the fuel and oxidizer are initially from separate origins. And perhaps the most classical or the obvious example of a diffusion flame is the candle. And typically, if the conditions are appropriate in the room, not too much current and so on, once it's ignited, it takes on a very stable form and usually looks like this. And it looks very simple, but it's actually a quite complicated process. And I really know only of one or two attempts to mathematically model or describe what's going on in a candle. Just generally speaking, if you look carefully at the bottom of the candle, once, of course, it's ignited and a flame is established, you will see a little pool of wax which has melted from the candle itself. And this wax is dragged by capillary sort of tension forces along the wick. And then because of the heat coming from the flame, it evaporates and the vapor diffuse out, oxygen diffuse in, and a diffusion flame is established. And then due to buoyancy effect, of course, it takes this elongated shape where the hot gases tend to rise. And you see that the temperature difference, you see here the temperature difference between different regions of the flame, probably the hottest. It seems to me that this part is missing. There was a temperature here which was a little higher than that. But anyway, and then different section of the flame with the soots and so on. So anyway, here actually the main reaction occurred here. The arrow didn't show. So it's about 14 Celsius, which is where the blue diffusion flame is established. Now, if the same flame under zero gravity will look a little different because it doesn't have this elongated shape, and it looks like almost a hemisphere, okay, which is a pure diffusion flame established by diffusion of the fuel vapor and the oxidizer from the other end. This was taken in various microgravity experiments, whether on the space shuttle or in drop towers and so on. Okay, so this is the topic today of diffusion flame. And when we started talking about premixed flame, we said, what is the simplest problem that we can think of? One-dimensional flame. In the case of a premixed, the flame propagates because it consumed the reactant. And so when it consumes some of the reactant, it has to move to consume the next layer of reactant and so on. In a diffusion flame, the flame does not propagate, does not necessarily travel unless it's done by forcing or other things, so instabilities. But naturally, you have the fuel, like in this picture, the fuel is coming from one end, the oxidizer from the other end, and there's a location where the flame is established. And so one would like to describe, Okay, I was going to discuss this. I'll go back to the previous one. So one would like to discuss the simplest problem in a one-dimensional setting. Now, in a one-dimensional setting, there is usually a mass flux of the gas, so it should go from one side to another. So I put it here. Mass flux is going in this direction, where this is the fuel, let's say. And you would expect that there is some fixed amount of oxidizer on far away on the other side. Unfortunately, this problem does not possess a solution. In other words, this is not, you cannot establish a stationary diffusion flame in this one-dimensional setting. The reason is very simple. The mass flux must be constant in a one-dimensional setting. The equation for the oxidizer is of this form. Very far away, there is no reaction. So the only solution of this equation will be a constant plus another constant, e to the m over rho do x. And since this should be C2 must be 0, because otherwise solution will go exponentially large at infinity, then the YO must be a constant. If it's a constant, it cannot satisfy both the far field condition, that it's a given amount of reactant, as well as 0, where it's consumed near the flame. So such one-dimensional solution cannot exist. Let me go back and then come back to this. So what I wanted to point out here, that one of the first analysis of diffusion flame was really discussed by Berk and Schumann. It's often referred to as the Berk-Schumann problem, or in a minute you will see the Berk-Schumann limit. And they have a very nice approach, a mathematical approach to describe diffusion flame. What they have done, they have looked at a problem in this configuration. You have two concentric cylinders. The fuel is coming from the inner cylinder, oxidizer from the outer cylinder. So you see initially they are two separated. And then you will have a flame established somewhere where the oxidizer diffuse in this way, the fuel diffuse in this way, and where they meet, the reaction occur. They introduced the idea, as I said, a very successful mathematical description, which has been known as or is known, if you like, as the fast chemistry limit. And they, in fact, coined the term diffusion flame. So nowadays, we say diffusion flame, it's equivalent to a non-premixed flame, but this was coined by Berk and Schumann. In fact, they introduced in their analysis a constant density approximation, which is something that if you say nowadays, they say, oh, you're talking nonsense, there is no combustion with constant density. But there are many things that we can learn from this. As long as you know what are the limitations of what you are studying and you know how to interpret it properly, then it has a lot of value. The way that they introduced that, they said that the mass flux in the axial direction is fixed. Well, it's the same thing as saying it has no effect on the flame and the flame has no effect on the flow, which is basically what is referred to as a constant density. So I already told you here that a steady planar diffusion flame cannot be sustained in an unbounded one-dimensional flow. Just to make sure that I clarify that statement, of course, you can have a situation where you have fuel in this side, oxidizer in this side, and you have a diaphragm that separates the two, and then you remove it, and they start mixing, and if the temperature is sufficiently large, they can even establish a flame, but the flame will be constantly, in other words, it will be an intrinsically unsteady process. That's not what I have referred to, okay? So I'm referring to steady flame. Okay. But some studies, starting with Brian Spaulding, well-known contributor to combustion in the early 60s and 70s, then by some other people afterward, they found a simple mathematical model that is useful to study diffusion flame. And it sometimes refers to as a chamber diffusion flame. Basically, instead of the problem being infinite, they do it as semi-infinite. So the fuel is coming, for example, from the bottom. It can come from a finite location or from all the way to infinity. It doesn't really matter. It's just a little detail. You know all the conditions in, let's say, at negative infinity. There is fuel, no oxidizer, temperature, say, is known. And at some location here, they specify the temperature. There is no fuel, and there is a certain amount of oxidizer. If you think about it, this is in principle not possible to maintain this concentration, because once you have a product diffusing out, it will change the concentration at that location. So this is not something that you can establish. In order to avoid these difficulties, when the model was introduced, they said, okay, there will be a very fast stream of oxidizer going across, washing out basically the product, and allowing for the oxidizer to diffuse in, not with no convection, so just diffusion of oxidizer. And then flame is established here, and it's a nice model. Of course, the question is, can you realize this model experimentally, because it's a nice theoretical construct, and it has been used both to describe the diffusion flame, but more importantly, later on, it was used to study instabilities of diffusion flames, which is hard to decide if you start talking about the candle or the Berk-Schumann problem, because the problems start to be two-dimensional, and then any perturbation to study the stability analysis make it even more difficult. So actually, since I have worked on that problem myself, I remember vividly that some very prominent scientists told, but this problem is not a problem because it cannot be realized. Well, several years later, with the help of some good experimentalists at the EPFL in Switzerland, it was established, of course, in a very, very smart way to do it experimentally. And what they did is they have the fuel. Here is the EPFL reference. So the fuel is coming from the bottom. And on top, in fact, this is even not the first model of that configuration, but so that the same is on top and bottom, but let me describe it. So on top, they have nearly 900 to 1,000 needles, very thin needles, the same one that are used maybe in medical application or medical needs. And the needles were separated at equal distance, and they were all at the same level, such that the oxidizer come in from the needles, and because there is a flow in this direction, the product is convected with the flow in between the needles. So the question still is there a, so you see here is the picture, basically. The oxidizer is coming here in the blue needles, and the product is leaving in between. And they did the same thing at the bottom with the fuel, but then the fuel may be convected with some velocity in order to have a uniform flow passing through the flame. So this was established, and that same prominent, that remain nameless, scientist admitted that this is a beautiful construct of what he thought was impossible at the time. So this is the way to establish a planar flame, and I'll show you the flame in a minute. But just to make clear that the boundary condition that the concentration of oxidant is a constant will clearly not be at the exit of the needles, but a small distance away, because it takes a distance for the flow to turn around and get uniform at that location. One more comment which is written here. The same problem can be looked at if oxidizer is provided or convected at the bottom, up and fuel diffuse, because after all, in a diffusion flame, if what you call fuel and oxidizer can be just arbitrarily. You can call this one fuel, this one oxidizer. You have two reactants that are basically going against each other. So here is a planar diffusion flame, which is established in that chamber. And here is the concentration of oxidizer. You see when you go to about 3.5 millimeter, the concentration is nearly constant. And that's the effective, if you like, boundary that mathematically we analyze the problem. And you see that the flame is rather flat. There is, of course, near the end, due to wall effect, heat losses, and so on, a little change, but otherwise it's perfectly flat. To make sure, there are flat flames, flat diffusion flames that can be established in the laboratory, but under, which is usually very common experiment, in a counterflow. In other words, when you have two jets impinging to one another, like the one I show for premixed flame, if you have the fuel coming one side, the oxidizer coming the other side, and the flow is diverging, then you have a flat flame. What's the difference? The difference is that in a counterflow, the flame is always under strain. There's always a stretch that the flame experience, whereas this flame has no stretch. Well, in principle, of course, experimentally, it will have a very weak stretch. And oh, I thought I had the measurement of the stretch rate. I didn't have it, but if you look at the measurements of the stretch rate, this is really minimal, except, of course, near the end. So anyway, there is a planar diffusion flame that you can establish. And now I want to discuss it or analyze mathematically the problem. So these are the boundary conditions. We already discussed them. For simplicity, I chose that the two temperatures are the same. It's very easy to generalize it and have two different temperatures. The mass flux, everything is in dimensional form here, so the tilde is dimensional. So the mass, the incoming mass flux is known. It's the initial density multiplied by the velocity. So this is a prescribed quantity. And then everything else here, you are already familiar. It's the same notation that I have used all along. The reaction rate, note that, of course, must depend on the product of the fuel and oxidizer. Here I cannot treat only one reactant, obviously. And rho t is a constant, which is from the equation of state is this. So I think the next thing will be putting the equation in dimensionless form. And note that I have emphasized here again that there is some kind of inherent symmetry in the problem. The same solution will result if I rename fuel oxidizer, oxidizer fuel. But of course, you have to be careful. You have to change everywhere where something related to the fuel is renamed and so on. So it's not important. So in dimensionless form, we are going to scale the speed with the incoming velocity, length with the thermal diffusion length, which is given here, thermal diffusivity divided by this U, pressure, temperature, and density with respect to their values, say initially in one region or another. And here are the equation. Of course, now you have two Lewis numbers, and these are the initial, the boundary condition, and the reaction rate, as we had before, equation of state. When you put it in dimensionless form, the parameters that appear quite similar to what we have seen before, but let's just make sure we emphasize them again. We have a Damn-Color number, which is the flow time. Now it's based on the incoming flow velocity U, divided by the reaction time. Note that it's inversely proportional to the mass flow rate. In other words, you increase the mass flow rate, you decrease the Damn-Color number. Then you have an activation energy parameter here, come from the Arrhenius term. You have the stoichiometric ratio, mass-based, which is new, which appears here in the oxidizer equation, because I make that one in the dimensionalization. And you have the heat release parameter, which is the total heat release divided by, say, the enthalpy of the cold gas. So the first approach that I want to do to solve this problem is use a unity Lewis number. In other words, assume that both Lewis number of the fuel and oxide is 1, and we will generalize that later. So this is 1, this is 1. The advantage is something that I mentioned in one of the first lectures. The mathematical operator on the left of the equation is all the same operator. Of course, here there's a minus omega, nu omega, and q omega. So the idea is to make combinations such that the omega cancel out. And you can make two linearly, again, I mentioned that in general, but I repeat, you can make two linearly independent relation, but there is always a third one that you can use. So if you add T to the mass fraction of the oxidizer, you get this second order equation. I think a Q is missing here. Yeah, sorry about that. You fixed the note, and there should be a Q here, so there should be a Q here as well. Okay? So those are two. And then if you subtract one from the other, you can get this differential equation. Okay? So, well, if you substitute, you will see that it's missing. And actually, when you take the difference, if there is no Q here, you don't get that. So you can check it. So anyway, there are three conserved scalars, and you can solve them easily. In fact, the solution of this equation is what I wrote before on the blackboard. It's a constant and an exponential, but now the exponential doesn't go all the way to infinity because the upper boundary is at a finite location. And so here is the solution of these three, okay? Of these three conserved scalars. It's straightforward. Okay, it's a common, the reduced number of equation, I mentioned that. So there is only one highly nonlinear equation that remain of those, let's say equation for temperature or one or the other, whichever you choose. But Berk and Schumann introduced a beautiful idea. They said that, well, the reaction would occur at a location where both the fuel and oxidizer are completely consumed, and therefore on one side of the reaction zone there will be no fuel, and on the other side there will be no oxidizer. And that really was a very nice, in fact, I would say even a brilliant idea at the time that allowed to describe the problem. Years later, it was recognized that this idea of fast chemistry can be more systematically described as an asymptotic limit in which where the Dam-Kohler number is infinitely large. The systematic approach, as I mentioned in one of my earlier lectures, helps in the idea that we can do more. We can later improve that idea, something that when you have an ad hoc approximation, it stops there. So anyway, if this is the Dam-Kohler number, flow time divided by reaction time, it goes to infinity. What it means is that the reaction time is very short compared to the flow time. And so immediately when fuel and oxidizer particle meet, they react. Okay? And mathematically, here is the reaction term. If D goes to infinity, for the reaction to be finite somewhere, then the product YF-YO must go to 0. In premixed flame, this is not possible, not very useful, but in diffusion flame, the product can be 0 if you have a region where there is no oxidizer and a region where there is no fuel. So the product is everywhere 0, except, of course, across or at the reaction sheet. So this is the approximation of that limit. Okay? Omega is practically 0 on this side, 0 on this side. And now this condition permit with the coupled or coupling function permit to define, in fact, everything. So if we start with this relation, which between fuel and oxidizer, where both vanish is at the flame or at the reaction sheet, which is x equal to xf. So this is 0, this is 0, e to the xf. You solve this for xf, you get this relation. It's minus the log of 1 plus a constant coefficient I call phi to the minus 1. If you look what phi is from just the combination here, you get that essentially it's the ratio of the fuel supplied on the bottom, oxidizer supplied on the top, divided by their stoichiometric ratio. People sometimes call it equivalence ratio. I don't know if it's a good term. In my opinion, it's not, because it's not like in a premixed flame that it's a parameter that describes the mixture. That ratio is only good at the two ends. If you come at different locations, the ratio is different. If you come at the flame, the ratio is 0 over 0. So it's not exactly an equivalent, but it's something equivalent, which tells you something at least about the strength of the mixture initially in the boundary. So I used to refer it as the initial mixture strength, okay? But it's something that you control. If the numerator is small, then eventually the mixture will be lean, or at least the system is lean in fuel. If the numerator is large, then the system is rich in fuel. So that's what it is. Okay. This is one thing you get from this relation, but you get more, because the region where YF equal to 0, that's a solution for YO. So here it is. And the region where YO is 0, that's a solution for YF. So in fact, this gives you the solution everywhere in the domain. And what about the temperature? So you take one of the other two relations that you can derive, the conserved relation. Where YF is 0, you get the temperature. So that gives you the temperature for x less than xf. And this relation gives you the temperature, because YO is 0, temperature for x bigger than xf. And what about finding what the flame temperature is? Well, it's the common value at x equal to xf, which you can evaluate from here or from here, and both will give you the same result, because, of course, xf is obtained from that same relation. So Okay, so this is the flame temperature, and we can, it will come in a minute. We can refer to as a adiabatic temperature, but I'll explain that in a minute. So here is the profile. The temperature rises to the flame temperature, the adiabatic temperature, and then it goes down to whatever the temperature on the end here, the concentration of oxidizer, concentration of fuel. What I was showing here is, I think for a later comment, is essentially that there is a slope discontinuity in the temperature and a slope discontinuity in the concentration at the reaction sheet, right? The slope essentially indicates that the heat conducted this way and the heat conducted that way. And the slope are not necessarily equal, so depending on the condition, more or less heat is conducted to one side or the other of the diffusion flame. And these slopes tell you the amount of fuel and oxidizer that are conducted into the reaction sheet. And there must be a relation between all these that we are going to see in a minute. So if I write the result that I obtained so far in terms of in dimensional form, this is the form of the adiabatic flame temperature, or the adiabatic temperature, or the flame temperature, T naught plus this quantity, and this is the flame or the reaction sheet position. For unity Lewis number, which is the case that we have discussed now, the adiabatic flame temperature, or the flame temperature, is the adiabatic flame temperature of a stoichiometric mixture consisting of so much fuel and so much oxidizer. It's easy to verify that. If you take these two quantities, you divide by them, you obtain that it's exactly the stoichiometric ratio. How did I get to these two values? Well, it's exactly the amount of fuel and oxidizer if you did not have any combustion, that at the location XF will mix together. Okay? So if the fuel in the absence of reaction or combustion will just behave this way to satisfy the two boundary conditions, the oxidizer in this way, and at that location, which is the XF under consideration, which is the place where, right, the amount that mix is obtained from here to be those. So this is the adiabatic flame temperature in this case. Let's see what how to generalize what we have said for non-unity Lewis number. So first of all the variables are expected to be continuous at the reaction zone. In other words, the reaction would occur at a certain temperature, and the mass fraction will be 0 at that location, okay? So you don't expect any jump. In other words, there's no jump in temperature at the reaction sheet. So this is the three conditions that come from that. The second condition comes from integrating this equation, which I cannot solve now because there is a Lewis number here. Note, by the way, that the Q is properly written here. So that this equation, of course, not for different Lewis number, I cannot solve them, but I can integrate them from one side of the reaction sheet to the other. In other words, I can integrate them from XF minus to XF plus. And if I do that, then I get the jump in the derivative of the temperature is related to the jump in the derivatives of the mass fractions, okay? And so this is another condition which is directly come from the equations, all right? Now, these by themselves is not sufficient because, look, we have a second-order equations, 3 second-order equation. It's a 6th-order system. We have 3 conditions, plus these are only 2. That's 1, and that's 2 linearly independent. So we have 5. And we need more condition to at least 6, but in fact 7, because we don't even know the location of the reaction sheet. But the idea that introduced by Berk and Schumann, that the product is 0, actually give us all the necessary condition, because it tells you that YF is 0 on one side, YO is 0 on the other side, and at the reaction sheet they are both 0. So here is, in fact, the simplified problem in that limit. Those we discuss, This and this gives you 2 more conditions. So now we have 7 conditions, 6-order system. We can determine everything, including the location of the reaction sheet. Just to reinterpret this condition, what it tells you is that the fuel and oxidizer which are coming from opposite direction or opposite side, flow into the reaction sheet in stoichiometric proportion. That's basically what these 2 relations mean. And it tells you something about the amount of heat conducted to one side, the other of the reaction sheet. Okay, so now we can re-examine the problem for general Lewis number, right? So now we cannot use the conserved scalar, but we have to solve each of these 3 equations, but it's the same type of solution, but with a Lewis number appearing in the exponent. So here is the solution for the fuel. It satisfies the condition at -infinity that it goes to YF naught. It satisfies the condition that at x equal to xf it's 0, because this is 1, so 1 minus 1 is 0. Same thing for the oxidizer. It's 0 at the reaction sheet, because xf is the same, so 1 minus 1 is 0. And at the boundary at 0, it's e to the 0 is 1, that goes, and this is y01 as it should. So it satisfied the proper boundary condition. Now remember, there was one condition. It tells you that the 2 flow in at stoichiometric condition, which is this condition. When you satisfy those jump, you evaluate this jump, you get the location of the flame sheet. Note that I called it XS, often referred to as the stoichiometric surface. It's the surface where the 2 meet in stoichiometric proportion. Of course, when Lewis number is 1, you obtain the same relation as before. But note that the location depends on the Lewis number. And it depends, in this case, on the Lewis number of the oxidizer, which of the 2 is not the one which is supplied with the stream, but it's the one that diffuses slowly against the stream of the fuel. If I have looked at the reverse problem, the solution will depend on the Lewis number of the fuel. In other words, if the oxidizer comes in the stream and the fuel has to force itself to diffuse against, the location will depend on that, because it has a difficult time to get further down. It comes only by diffusion, as opposed to the other reactant, which also is convected. So this is the location. What about the flame temperature? Okay, I said that. The flame temperature, so we can solve also this equation for the flame temperature. The flame equation doesn't have a Lewis number, so it's simply the exponent. And those 2 conditions satisfy the fact that at -infinity, t goes to 1, e goes to 0, and at x equal to xs at the stoichiometric surface, T is the stoichiometric temperature. We don't know it yet. It's a stoichiometric temperature. Similarly, on this side, where x equal to 0, it's at the boundary, T is 1. And when x is equal to xs, again, is the stoichiometric temperature. So the next step will be to determine the stoichiometric temperature. But remember, there was one more condition, that the jump in dt dx is the same as either the fuel or the oxidizer. And so when you evaluate it, you get an equation here, which is essentially the flame temperature or the stoichiometric temperature. Of course, you're going to obtain the same thing if you use this one, because the fact that we have used the fact that this and this is equal to each other in order to get excess. What is important to note here again, something which is not perhaps very widely mentioned or emphasized, is the fact that the stoichiometric temperature depends on the Lewis number. In other words, it's not the adiabatic flame temperature as for unity Lewis number, and moreover, it depends on the Lewis number of the oxidizer in this case, for the same reason that I've mentioned before. So unlike premixed flame, where the flame temperature for all Lewis number is always the adiabatic flame temperature of diffusion flame depend on the Lewis number, which means on the means in which the fuel, in the way that the fuel and oxidizer are brought towards the reaction sheet. Only for unity Lewis number you obtain the adiabatic flame temperature. The condition across a reaction zone in general can be obtained by, can be also, I mean, the idea that I've just presented can be generalized for a flame sheet which is not necessarily plane. So I show you the result for a simple condition. Suppose that you have a curved or a flame like this, then the fuel and oxidizer will coming at different direction. So these jumps have to be satisfied in the normal direction to the sheet. So you just change the gradient here to the gradient in the normal direction, and everything else remains the same. And so this is a summary of, if you like, how to treat the reaction sheet in the limit. Remember, it's the Berk-Schumann limit, but it's the limit of Dam-Kohler number D goes to infinity. The fuel and oxidizer are completely consumed at the sheet. That's a summary of the thing. The temperature and concentration are continuous at the sheet, and the net fluxes to the reaction sheet are diffusive. That's why, by the way, it's referred to as a diffusion flame. The fuel and oxidizer fluxes are in stoichiometric proportion, which is what I mentioned here. And this is written in dimensional form, so you can apply it to any condition you like. Let's now look at the problem that Berk and Schumann did. At least for historical purpose, it's important to examine it, but it's also an interesting problem that, because it's already not a flat flame, it has a more curved surface, so it's interesting. So these are basically the assumption that Berk and Schumann did. The flow is assumed to be parallel, so it goes only in the z direction. Remember, this is two axisymmetric cylinders, so we use cylindrical coordinates. And the velocity field is given by v equal to some given u in this direction. So the velocity is fixed. The mass flux in the axial direction is assumed constant, so rho times u was taken to be constant, as I told you earlier. Berk and Schumann used the assumption the Lewis number are both equal to 1 because it simplifies the mathematics, as you will see soon. And axial diffusion, and that's a very important assumption in trying to solve the problem. They assume that the axial diffusion, in other words, diffusion in this direction, is negligible compared to diffusion in the radial direction. Now, why is that important? Because normally what you would have here is the Laplacian of yi, and the equation essentially is elliptic, and it's more difficult to solve an elliptic equation. And when you neglect the part of the Laplacian in the z direction, you get a parabolic equation, which is much easier to solve. Even numerically, you solve it by marching, and you don't have to do more complicated approach to it by iteration and so on. But there is more to it, and here is another comment. There will come the appropriate boundary condition that they have chosen, because it's a parabolic system, is that along this location z equal to 0, there is no oxidizer in this region, which is that between 0 and A, there is no oxidizer. Between between A and B, there is no fuel. And of course, along these walls, the fluxes are 0. There is no penetration of reactant. Now, why is that emphasized here appropriate for this parabolic system? Because if you allow for axial diffusion, you cannot use these as your boundary condition because there is upstream influence. And so there would be some diffusion, that backward diffusion that can affect the solution. In other words, you cannot prescribe your condition at x equal to 0. Things can diffuse axially and then down below the, in fact, you will see this in another example that I will be doing later today. So what you then have, well, they introduce dimensionless variables. So here is the equation in dimensionless form. And, you know, everything is almost obvious. The coefficient C, it's the ratio A over B. So it's like the distance of the small cylinder compared to the big one. The big one is scaled to be 1. So there is only fuel in the inner cylinder, only oxidized in the outer cylinder, and those are the conditions like before. And so since they use the unity loose number, the operator here and here are the same. So the difference between YF and YO effectively is a conserved scalar that's called psi. Okay? So psi is the conserved scalar here, and it satisfies a linear equation that you can solve. In fact, this is nothing more than the heat equation classically solved in various settings. So the boundary condition is psi equal to 1, and psi equal, when you put this in dimensionless form, it's exactly what I have called before the initial mixture strengths, which tell you something about the relative ratio of the fuel inside the inner cylinder and the oxidizer outside. So you want to solve this equation. It's solved, I'm not going to show a lot of the details, solved by separation of variables, and you get a solution which of this form, an infinite series here, A are coefficient. This is the Bessel function of 0 order and exponential, and lambda n are, when you do separation of variable, of course you have the separation constant, gives you eigenvalues, and so lambda are the eigenvalues, and the eigenvalues to satisfy the boundary condition turn out to be the, where did I say that, the roots of J1, which is the Bessel function of order 1, so lambda n satisfy this, and in fact there is a graph here of J0, J1, and J1 is the green one, and so it has all these roots that you can determine, and so you can evaluate the solution. Note that, by the way, A0 and the AN are slightly different, but that's a detail. Now, since we know the solution, the location where YF and YO are both 0 gives you the location of the reaction sheet, right? That's where the reaction sheet is. So YF and YO equal to 0, this is psi, makes psi equal to 0. So psi equal to 0 gives you a relation which is a functional dependence of R on Z, right? In other words, like a function R of Z equal to 0, which is a surface in the three-dimensional space, or axis symmetry. So in principle, you have an equation that you can plot to obtain the surface, and then if you know that, you can of course where YO is 0, psi represent the fuel, where YF is 0, psi represent the oxidizer, so you can get those. But we are interested more in the location of the reaction sheet. And so if you take this relation and you evaluate, you can see it will represent, as I said, some surface. And the surface could have two shapes. Either it can converge towards the center, and therefore h will represent the height. Now the height in this relation would be when r is equal to 0. So when r equal to 0, you get an equation here. Of course, it's an infinite sum that tells you the height. And when it takes this shape, okay, then the height is given by r equal to 1. Okay, so r equal to 1. If you notice before, I don't want to flip back, but the eigenvalues become smaller and become larger and larger as you add more and more of them. And of course, since they appear in the exponential, the contribution, the infinite sum becomes small. So it makes sense to try to take few terms in the series just to get a quick sense of the approximation. So if you take two terms, for example, that's what you get. And so immediately you can find the height for what is referred to as under-ventilated flame, namely those, okay? That's when r goes to 1. In this case, only lambda 1 is important, and that's the value. And if you try to get the height for over-ventilated flame, then you get you set r equal to 0 and you get this relation. Well, anyway, those are the two possibilities. And if you examine the height depending on the reciprocal of that parameter phi, the mixture strength, or the initial mixture strength, you find that when, let's see, when phi is large, phi large meaning relatively rich, then you get an under-ventilated flame, okay? And when phi is small, you get an over-ventilated flame. Because when phi is large, there is it's rich, and so there is a lot of oxidizer diffuse in this direction, so flame tend outward, and otherwise it will tend inwards. Okay, so this is the solution of Berk and Schumann. They provide 1920. It's quite early in the development of combustion science. Later on, it was discovered that, as I said, was discovered that the Berk and Schumann idea is in fact the limit of d goes to infinity. But I think I mentioned to you all along that when you have a discontinuity, principal discontinuity, have to be smoothed out. And so there must be a structure that connects the slope that are discontinuous from one to another. And this you can do by idea of boundary layers or in using asymptotic. This was done much later in the development, and I want to describe that first. So the equations are again written, the same dimensionalization. Everything is, I think, the same as before, with one exception, that we rewrote the Dam-Color number by multiplying it with the e to the positive e over RTS, and multiplying here the exponent with e to the minus e over RTS, which using the beta defined here will be of that form, okay? In order to multiply and divide it by the same factor. And so this is what I more likely like to call the reaction time, not only the pre-exponential factor, but the exponent with it. And Ts is the stoichiometric temperature, which we only know when we compute the problem, okay? It's not a given quantity. Okay, so, and the Dam-Color number, again, is inversely proportional to the mass flow rate, and that's what it is. Okay, so when we analyze a general surface, we have to stretch the coordinates in the direction normal to the sheet. Okay, this just indicates that in that limit there is no oxidizer here, no fuel here, just to set up the configuration. So the two regions on both sides of the reaction sheet are convective diffusive regions, right? No reaction, and then the reaction occurs in the thin layer here. So we stretch the coordinate n, and I would not show much the detail, but just the general idea. So n is stretched by a small parameter epsilon, which indicate the thickness of that layer, but we don't know it yet. YF and YO are near zero, so we perturb them around zero. T must be perturbed around the stoichiometric temperature, Ts, and rho, of course, come from the equation of state to be related to T, so it takes this value. And so when you substitute this in the reaction term, you get Damn-Color number, rho s squared. That's the leading term in the density. This is the leading terms of YF, YO, and the exponent come to be e to the epsilon beta x. Okay? Sorry, not x tau, where tau is the perturbation of the temperature. So we substitute in the equation in order to find what is the proper balance. And so when we substitute in the equation, we already seen that usually in thin layer, the diffusion become more important than convection. So the diffusion turned out to be the more influencing term. And on the right-hand side, and I probably, I have the Q. So on the right-hand side, you get what you get here from here. So you have the Damn-Color number. Then this epsilon cube comes because there are epsilon here, so epsilon squared. And one of them come from the fact that we stretch the coordinate, and in fact, two of them, but there is another epsilon in the numerator, so that gives you epsilon cube. Anyway, in order to balance this equation, you expect that this should be order 1, so that both sides are of the same magnitude, which means that epsilon has to be, in principle, Damn-Color number to the minus 1/3. The fact that I put here rho s just makes simpler the mathematics or the presentation, but nothing more. So the thickness of the Berk-Schumann flame sheet is the Damn-Color number to the minus 1/3. And then the equation that you have to satisfy is this. Okay, but this is one equation for the temperature. Similar equations can be written for, we are about to end the lecture, right? Okay, just 1 second. So similar equation have to be written for the fuel and oxidizer. And there is another typo here. I noticed this should be YF, this should be YO, or vice versa. Yeah, no, this YF, this should be YO, or correct it if you want. And then it's not difficult to show that for any outer solution, in other words, no matter what the flow outside is, the problem can always be reduced inside. In other words, in the layer, can be reduced to this canonical equation. Of course, it takes some transformation to go from one to another, but you have a canonical problem, canonical boundary value problem, does not depend on any parameter, okay? So it can be solved once and for all. Unfortunately, this problem cannot be solved analytically, but you can see what happened. By the way, the slopes are plus or minus 1. You notice that there is a transformation that took the different slope and scaled them to be negative and positive 1. And positive negative 1, you can see from here when, say, phi goes to zeta and phi goes to minus zeta are in fact those two straight lines because they will immediately satisfy this equation, but they don't satisfy identically because they must curve somewhere. So you integrate this equation, that's what you get. The solution is this dashed red curve that tend properly to the two asymptote. this solution always exists. And so the beauty of the Berk-Schumann solution is that you can always have a structure, it always exists, it always connects properly those slopes, okay? So that's very nice. One thing that, and the thickness of the layer is this. Now, one thing that I want to say before we take a break, and then we will take a break and continue afterward, is note that in constructing here this right-hand side, e to the epsilon is small, e to the epsilon is 1, so was approximated to be 1, so it does not appear here. In other words, nothing was mentioned about the activation energy. It was treated as if it was an order 1 quantity. And so the reaction zone in the Berk-Schumann limit is temperature independent in a way, okay? The next development was to make the difference with beta. In other words, treat also the activation energy to be large. That will come after the break. Okay, we will continue. So in summary, what we have seen is that we can actually construct the structure in the thin region that describe the reaction sheet in the limit when d goes to infinity, or the structure of the Berk-Schumann solution, and it always exists, so it doesn't provide any limitation or any restriction on the solution. The solution, if you use the Berk-Schumann, it will always exist. Of course, the solution is good, but it's only limited to complete combustion, and so of the reactant, and so what it does not show, or at least the limit does not show, some dependence, what did I see here? Some dependence on the temperature. Well, I said it doesn't explain extinction, but basically, the last comment before leaving for the break, I mentioned that the exponential was written as e to the epsilon beta tau, the temperature. And so when epsilon goes to 0, it goes to 1. And so the structure is sort of isothermal, if you like. But that's a limitation in certain way. So actually, that's what's written here. What has been missed is the sensitivity of the reaction rate to the temperature. This can be retrieved when we examine two limits or a distinguished limit, that both we treat d, the Dam-Kohler number goes to infinity, as well as the activation energy parameter going to infinity, becoming large. And this was first described by Linian in a very detailed discussion of a counterflow diffusion flame, but was limited to unity Lewis number. And later it was more generally established for a multidimensional, in other words, not necessarily the counterflow, but any surface, if you like, and more importantly, non-unity Lewis number, okay? So the idea goes as follows. And again, we take the sheet, we stretch it near the, we stretch the coordinate near the reaction sheet in the normal direction. We perturb the fuel and oxidizer like before, and the flame temperature like before. Everything is here like before, including the approximation for omega. But now d is large. We also want to assume beta is large such that epsilon beta is order 1, and therefore the temperature will enter into the equation. So if epsilon beta is order 1, it means epsilon is like the reciprocal of beta. So now you see the reaction, the thickness of the reaction zone is not Dam color to the minus 1/3, but it's 1 over beta. And the distinguished limit tells us that the Dam color number must be such that epsilon cubed times d is a modified or a modified Dam color number, which I denoted by d hat, and that's a distinguished limit. So there are two limits that must be connected, and now this is retained. So now you see the equation for the structure is more complicated, but it depends on the temperature. Again, we can write other equations for the fuel and oxidizer similar to this, and then manipulate this equation. It turned out that now, when you try to use some transformation to write the problem in a simple canonical way, it turned out that the problem depends on two parameters, delta here and gamma here. So for any outer flow, which dictates the value of delta and gamma, you always can reduce the problem to a single equation, which given gamma and delta, if you solve it, you describe the structure, okay? So I will, and note, by the way, that the slope again has to go to plus or minus 1. So I will, I think I will describe first the solution of this, and then, or at least discuss part of the solution or what schematically it should be, then show you solution, and then talk about what delta and gamma are. Actually, I did it the reverse. I talk first about delta and gamma and then show. So what is delta? Delta is effectively a reduced Dam color number. It turned out to take this form, okay? It depends on the, you see, on the jump in the temperature gradient. In other words, it tells you the temperature gradient tells you the difference between the heat conducted, because the slope of the temperature, one is positive, one is negative. It means that heat is conducted in one side in this direction, the other side in this direction. The difference is that quantity. So given the outer flow, which may be whatever it is, a droplet, a spherical flame, a Berk-Schumann flame, you can always compute these quantities, and you create the delta. Also, the delta depends on HF star, which is quantities that will be determined from solving this boundary value problem. But let me describe them in words now, and you will see what I mean later. I refer HF as the degree of incomplete combustion, or the enthalpy, the local enthalpy of the mixture in the reaction zone. It depends on the deviation of the flame temperature from the stoichiometric temperature. Remember, stoichiometric temperature is temperature for complete combustion. It depends on how much fuel and oxidizer leak through the reaction zone. Now, we may not have complete combustion, so some may leave the reaction zone. And I will show you how these are determined in a minute. And the second parameter, gamma, is only a heat transfer type of parameter that you can compute. So if you know the outer flow, in principle, you can determine these two parameters. Note that I said that gamma is -1 to +1. When gamma goes to one or the other limit, so the temperature profile are basically one positive, one negative. When gamma goes to either -1 or +1, don't remember which is which, you get a structure, you get a temperature which is go like that. In other words, the slope here is 0 on one end to another. Linian referred these to premixed flame regime. When gamma is between -1 and 1, you get two slopes, and this is what he referred to as the diffusion flame regime. And I'm going to focus on the diffusion flame regime. The others are obtained only if you heat up say the oxidizer to a sufficiently high temperature close to the stoichiometric value, or you heat up the fuel to such level. perhaps in some other condition, but that's generally what it is. So that's this limitation. Okay, so now, given a given problem, we know delta and gamma. We want to solve this boundary value problem. And there is, unfortunately, I think, a mistake in the picture that I have put in your notes, simply because when this was done, and I always encourage you, don't rely on notes, go look at the paper itself, because I think when it was done, the transformation was made such that it reversed the direction of fuel and oxidizer, and that was not the intent. So I tried to reverse it back. So anyway, there was some typos there. So this is the picture. Now you see it's reversed because I like to have the fuel from the left, oxide from the right. But anyway, so the key point here is that the slope has to go to plus or minus 1, which means a line parallel to the green and parallel to the blue. So I put here a dashed 1 and a dashed 1. I'm schematically showing you how the solution of this boundary value problem will be constructed, and then we will see the numerical solution. And, but it does not say that phi has to go exactly to the coefficient here, or the independent variable, which is, in this case, zeta and minus zeta, right? So there must be some deviation. And that deviation is turned out to be exactly proportional to how much, in this case, oxidizer is leaking, in this side, fuel is leaking, okay? And so this is that picture. And note that this is the temperature, so the flame temperature, well, I don't know, this region is infinite, so where do you define the flame temperature? You can, the most reasonable thing is to define the maximum value in this regime. But if you define it slightly to the left or slightly to the right, remember that this is an epsilon quantity, so it really doesn't affect the value, okay? It's a minor change in the value. It's still a good representation. After all, if you have a diffusion flame and you think about it to be a finite regime where the combustion occurs, what is your definition of flame temperature? One choice could be the maximum, but it's an arbitrary choice. You can always define it a little bit to the left or at some location and so on. So anyway, that's this. And here is the amount of fuel and oxidizer that leak, precisely given in terms of these function SFSO. Now, this boundary value problem is second order. It only requires two boundary conditions, which is the slope. And so once you solve the solution, this S1 and S2 are obtained as part of the solution. So if they're obtained as part of the solution, then you know the leakage, okay? So as I told you, there may be inconsistencies between what I wrote here and what's in your notes. Be careful. So now here is the numerical solution. And note that this is for gamma equal to 0. Maybe I should make a couple of comments here. First of all, when delta is infinite, okay, delta to the minus 1/3 go to 0, e to the 0 goes to 1, and what you see is exactly the Berk-Schumann structure, okay? So when delta goes to infinity, you should recover the Berk-Schumann structure, and SF and SO, which represent the leakage, should go to 0. The second comment is not obvious, but if gamma is, well, if gamma equal to 0, it turned out the problem is symmetric on one side or another. In other words, equal amount of heat conducted to the fuel and the oxidizer. And when gamma is positive and gamma is negative, there is a relation that can be established. So it's enough to solve numerically the problem only for either gamma positive, gamma negative, and then you have the answer for the other. And so here is the solution. But what do you see in the solution? Let's start with a very large Dam-Color number, delta equal to 10. One of the solution is here, which approach very much these two slopes, which are the Berk-Schumann limit. It turned out that there is another solution, but this is more obvious when you go to smaller values, because when delta equal to 10, the other solution is below this one. When delta equal to 2, you see here is one solution, which is the light blue, and there is another one here. You don't see the rest, but it does satisfy properly the condition. When delta equal to 1, you very clearly see the two solutions. When delta equal to 0.9, again, the two solutions, they keep on approaching each other. When delta reaches this point, 84947, you have only a single solution, which is the red curve. And if you reduce delta below that value, you cannot find solution for this boundary value problem. There is no structure. There is no solution. So the solution, first of all, exhibit the anticipated symmetry, what I mean when gamma equal to 0. Two solutions exist when delta is above a critical value, and none when delta is less than the critical value. And just to show solution for different value of gamma, you see what you notice is what I have referred to, that distance between the slope and the slope zeta minus zeta. And in other words, the leakage here is larger than here. So there is the degree of leakage depend on gamma, okay? So, but you still have two solutions for delta above the critical value, and the critical value change, of course, with gamma. So what are these two solutions? It's clear from these, since these are temperature, that the difference between the two solutions, say this and this, it's the flame temperature, however you define it, okay? So this one has a lower flame temperature than this. And so when you go to the when I plot the flame temperature as a function of the Diamond-Color number, here are the two solutions, the higher flame temperature, the lower flame temperature. And when you get to the critical delta, which is associated with some critical Diamond-Color number, that you have a unique solution and no solution to the left of it. And when d goes to infinity, or delta goes to infinity, you approach the Berk-Schumann limit, or the stoichiometric temperature. And so essentially, this is a sketch of what you get. The Diamond-Color number is very large. You have the flame temperature is the stoichiometric, and as you reduce the Diamond-Color number, in other words, you increase the mass flux towards the flame, then the flame temperature decreases. At the same time, the degree of incomplete combustion with leakage on one side or another, depending on gamma, reduce more, up to a certain point. If you try to decrease it below, flame is gone, and that point can describe extinction. So the nice thing about the distinguished limit of incorporating large D and large activation energy is the ability to describe the entire spectrum from complete combustion all the way to extinction. These are just to show you what the leakage function look like, fuel leakage, oxidizer leakage for certain gamma. If you, again, this may be not correctly presented in the notes, sorry about that. But anyway, when gamma is negative, it's the reverse that happens. So this is the structure, and it can be applied to the planar flame, for example, that I showed you before, and it will show conditions of incomplete combustion all the way to extinction. It can be applied to other problem which like the droplet problem that I may talk about later to some extent. And therefore, it's a useful representation, also describe the structure of the reaction zone properly. I want to make some comment about the mixture fraction formulation, which is often used in the literature. And I will try to be brief to move on. So consider you have a stream of two streams, a fuel stream that I call 1 and an oxidizer stream that I call 2. They're coming from two opposing directions. We assume that there is no fuel in the oxidizer stream and no oxidizer in the fuel stream, so we have a diffusion flame. Of course, they may contain some inert, so it's not pure fuel or pure oxidizer. And one can define what is known as the mixture fraction, Z, which is defined as such. More or less, it's the conserved scalar YF minus YO. But it's also scaled in such a way that Z equal to 0 in the oxidizer stream, because in the oxidizer stream, YO is YO2, so this is 0, and there is no fuel, so YF is 0, so Z is 0. In the fuel stream, YF is, what did I say? That's in the, yeah, the oxidizer stream. In the fuel stream, YF is YF1, but there is no oxidizer, so this is 0. And so you get new YF1 plus YO2, which is the same as the denominator, and Z equal to 1. Of course, it can be determined in more general way, but for our purpose, more general way, I mean not only for two reactant mixture fuel plus oxidizer product, can be described in more general way. In fact, it's described by taking the fraction of the total amount of some material, fuel, present that came originally from the fuel stream. Okay. Z, of course, is a variable that depends on position and on time, the same way as YF and YO are. Now, the mixture fraction, one can write an equation for Z, but, well, if we start with the fuel and the oxidizer equation, and we construct Z and we substitute in here. Of course, you know that if the diffusivities are the same, which is the same as saying Lewis number is 1, then the difference between the two satisfy conserved equation. Well, if it's not, if they are not equal, then you can manipulate to write that you have an equation that depends, say, on one of the diffusivity and the difference between the other two diffusivities, okay? So, but this is just a writing, because all I wanted to say here is that the diffusivities are equal, then you can get a single equation for Z with a diffusivity, which is the common diffusivity, which I have written here. So you can always derive an equation for the mixture fraction. Note that it's a function of space and time. The interesting thing is that if you, since you expect the reactant to depend well, you can rewrite, let's say this way, it's phrased better in the slide. Since in the fast chemistry limit omega equal to 0, then the equation for the fuel equal to 0 can be also expressed in terms of thinking of Z being a function of x and t. You can always express yi in terms of this function Z, which also depend on x and t, okay? It's just a transformation, if you like. And if you do that, then you have to do the chain rule and so on, because dyi dz, say the derivative of yi will be dyi dz, and then the derivatives of z by the chain rule. So when you do that, you obtain that this equation equal to this dyi dz and the rest. Now, since Z satisfies this equation, that's 0. So the end thing is that yi satisfies second order equations with respect to Z. So it's a linear function of Z. Yi are linear function of Z. And so you can construct those based on the fact that this y has to be y02 here and yf1 here, and Z is defined like this. So you obtain the two straight line dependence on Z. So in terms of the mixture fraction, the mass fraction can be simply presented as a straight line in the limit, of course, of infinite chemistry, where everything is consumed at some location, which will be represented by Z stoichiometry. Okay? Z stoichiometry is where YF and Y are both 0, so it's Y02 divided by that. Okay, so this is one thing to note. If in addition, not only the diffusivity are equal, also they are equal to the thermal diffusivity, so that the Lewis number is 1, then you can also write, remember, two coupling function, which is a combination of T and YF, T and YO. I call them HF and HO, which is like the partial enthalpy associated with the fuel and the partial enthalpy associated with the oxide. That's basically what they are. And so one can show that similarly HI are also linear function of Z because these equations are conserved, okay, conserved scalar. So you can therefore write in detail the linear function that satisfy the proper boundary condition, with T1 and T2 being the two temperatures on the left and on the right. And in addition, you can also obtain the flame temperature by evaluating this at Z stoichiometry, which we found in the previous slide, right? And so clearly that what you obtain here, since it's unity Lewis number, it's exactly the adiabatic flame temperature. In other words, it's independent of the Lewis number. And this is exactly the same adiabatic temperature that I derived before, with one slight modification, that here there are two temperatures, T1 and T2 of the two streams. If T1 is equal to T2, you see that you get here the T naught, and that's what we derived before. Okay, so this is the adiabatic. So here is the picture. You have also the temperature are straight line. So there is a simple description of the entire flame, or the profile of all the flame, or the solution, if you like, in terms of the mixture fraction Z. In fact, you can also construct the frozen limit. Frozen limit meaning that there is no combustion, or the reaction is 0 everywhere. So what is no combustion? It means just pure mixing. So the pure mixing is described by these two lines. It's also a linear function of Z. I'm not sure that I need that in the discussion, but anyway, it's here. So this is the complete combustion. So it's beautiful if I knew how to, what is Z, but in principle, Z is a function of space and time. So it's not always useful. But if the combustion field is expressed in terms of one coordinate, and the density variation have a negligible influence on the fluid dynamics of the flow, it's convenient to make a change of variable and use Z as the transformed coordinate. Instead, for example, if you use the counterflow problem, which is an example I think I plan to show. I don't know if I will show, but anyway, so there is in the counterflow, then what you have is two streams, right? The fuel and oxidizer, and so the coordinate here goes, x goes from, say, -infinity to +infinity. If you use if you want to construct Z, what you do is a transformation from X to Z, okay? And then the linear profile that I had before is the solution, but for the infinite Damn-Color number, remember. But how do you do the transformation? Well, you have to solve the Z equation. So for a counterflow, 2 epsilon, if it's axisymmetric, as I did in the premixed case, 2 epsilon is the strain rate, and so this is the equation for Z. When you solve it, you get 1 minus the error function, and so Z is nothing but contracting the minus infinity infinity to 0, 1. Just a simple transformation. But I had this already. But in general, Z is not quite a coordinate. So if it doesn't vary very much, then you can say, okay, then the flow field is described by the mixture fraction, and so you think of the mixture fraction as being one of the coordinates. But take, for example, the mixing layer when you have a fuel and oxidizer separated by a splitter plate, and then some flame get established here, something that we will discuss later today, yeah? And so if you really evaluate, if you solve the Z equation for this problem, even under the condition that the flow is uniform, in other words, uniform in both direction and no thermal expansion, what you get is these curves that you see, these parabolas are constant Z. So the Z coordinate will be something which is not a straight line. So saying that the combustion field vary along the mixture fraction is not really in the simple direction, but it's in some curved direction. And clearly that is known a priori, so if you experimentally argue that this is the solution in terms of the mixture fraction, it's not clear how to interpret that. That's basically what the point I want to make, okay? So it's a useful concept, but it's limited in a way. Okay, just the last comment, which is of interest, is that I can use a transformation from XYZ. This was done by Norbert Peter in an early paper on these ideas, that you make a transformation from one of the coordinates to this mixture fraction Z. Then this implies that the unit normal to the stoichiometric surface, this is for a 3-dimensional surface, is effectively, because the surface is Z equal to Z stoichiometry, then the normal is the gradient of this function, which is Z minus Z stoichiometry, which is the gradient of Z divided by the norm. So what I showed you before in constructing the structure, instead of taking the function that described the surface and using the normal defined based on that surface, you can relate it to the mixture fraction. If you do so, then your structure equation just get here an extra factor, which is the gradient Z square, which must be evaluated at the stoichiometric surface. And so it just changed a little bit the reduced Damn-Color number that I called delta. This quantity in the literature is referred to as the instantaneous dissipation rate. And so if delta is below a critical value, the flame, we have seen the flame get extinguished. So in terms of the dissipation rate, it will be if chi is bigger than some critical value, the flame will be extinguished. So it's really a rewrite, if you like, of the result in terms of this mixture fraction. So anyway, I'm not going to elaborate on this. It's a useful concept, but with limited use. I think this is the end of this lecture, and now I'm not sure. This is lecture 2 of today. Let's see. This lecture goes on. I'm sorry, I get confused because at the university, the hour always started the hour and then 10 to the hour. And now I always have to think what it is. So we started the second one. What time? You help me there. When do? 11? Yeah. Exact. Okay, fine. So this one I will run quickly and skip some stuff. I wanted to show the example of a counterflow. So this is essentially the counterflow, and we will consider first essentially in a constant density setting. So and then I will talk about later the effect of thermal expansion. So the flow is known and is given essentially by 2 epsilon x, but epsilon is the strain rate. And when you scale it, the epsilon appear in the Dam-Kohler number. So the Dam-Kohler number is proportional to the reciprocal of the strain rate, okay? And everything else is very similar to what the discussion before. If you look at the frozen limit, namely D goes to 0, no reaction, it means pure mixing. You get simple profile, very similar to what we have discussed. In this case, we have taken that the temperature is the same on both sides. And if you take the Dam-Kohler number go to infinity, or the Berk-Schumann limit, you can write an explicit solution which looks like this for the temperature and something similar for the mass fraction. And if you numerically solve the problem, not taking this limit, but just numerically and using a large number for D, you obtain a solution that you see very similar to what the structure have shown, namely smooth out the discontinuity. And you can write equation for the flame temperature, which is now the stoichiometric temperature. Note that it depends on the Lewis number, both of the fuel and oxidizer, because XF, which is the location of the flame, depend on both Lewis number, and so similarly the flame temperature will depend on this. I'll skip that. This is just quickly to show you that when the Lewis number is 1, then and when phi is equal to 1, then this is the location of the flame or the stoichiometric surface. So it's going to be on the fuel side when it's a lean system, phi less than 1, and on the oxidizer side when it's a rich system or phi bigger than 1. However, if the Lewis number is bigger than 1 or less than 1, then whether it sits on one side or another depend also on the Lewis number, because depend how the fuel and oxidizer diffuse to reach the reaction sheet. And the temperature, you see the red curve, which correspond to LF equal to 1, is the adiabatic flame temperature. Of course, it depends on phi, but you can have super adiabatic flames for low Lewis number and sub-adiabatic flame for Lewis number bigger than 1. And so this was the frozen limit, T0, and this was the Berk-Schumann limit, which we computed. The flame temperature was Ts. So in principle, the Dam-Kohler number, as you increase the Dam-Kohler number from 0 to infinity, you should have a curve that connects those two limits. Perhaps the curve is like this. Perhaps it is like that. In fact, it turned out that it's more The more common one is the S-curve that you see in red. It was first obtained numerically by Fendel in '65, but then the activation energy asymptotic limit can actually describe, well, we have seen that it described this part of the curve, and one can also describe this part, which would correspond to essentially an ignition limit, which is described here. So what you have here is that if you reduce the dam color number from very large number, we have seen that the flame temperature is decreased. There is more and more leakage of fuel in oxidizer from both sides of the flame until you reach this value. And if you try to lower the dam color number more, in other words, you increase the flow rate more, there is no solution, so you drop to only the possible solution, which is the frozen limit, no reaction. On the other hand, if you start from the frozen limit and you keep on increasing the dam color number, come a point where there is no solution here, and you necessarily jump up to a complete combustion, or at least near complete combustion, which is an auto-ignition, an automatic ignition that occurs. So this is what I wanted to show here. And now, if you look at the solution of the counterflow, but account for the thermal expansion, so you see now we are incorporating the mass, the continuity equation with the density variation and the momentum equation. The problem, by the way, admit a similarity solution, and so it reduced to only a dependence on x. Sorry, I cannot show you all the details of this, but here is what's interesting. You see, in the absence of thermal expansion, or if you don't have a flame, the flow field in a counterflow will be just this dashed line that goes through the origin and here, okay? It's the symmetric solution that go all the way. It's a straight line that decrease in the axial velocity all the way to 0. But in the presence of combustion, you have a flame somewhere, there is a displacement. You see there is an increase in velocity, and then it must go to 0. And similarly here, a decrease, but on the other direction. And so this displacement, delta F and delta O, it's a displacement due to thermal expansion. And these are displacement when you change the heat release. Of course, it's more significant. It's small when heat release is small, and it gets larger and larger, because the more the heat release increase give you a change in a more significant change in density. And these are curves that show the fuel and oxidizer leakage computed from the asymptotic theory, which is the dash curve, and from the numerical solution, which are the symbols. They are not, of course, identical, but they show similar trend. Note, however, that these numbers are rather small, but the graph intended to show the differences rather than to show that it's a beautiful agreement. After all, beautiful agreements are seldom, even if you do very careful computation. And that's the same thing for the flame temperature with the turning point that describe extinction. Okay. The next topic was intended to, or is intended to describe, to discuss droplet combustion. And I will be again, I will skip few things. First of all, I wanted to say that, you know, if you have a spray, you spray the fuel, the idea is that you want it to break into very small droplet because they will have more surface area than the liquid sheet that you will in the jet. Rayleigh early on showed that if you look at a sheet of fluid and you do a small perturbation, then lambda is the wavelength of the perturbation. show that due to surface tension, you get an instability. And he described, in other words, the sheet will not remain smooth and straight, but it will start developing perturbation on its surface, which, if you stretch out a little bit the theory, in other words, you take it to extreme, then this perturbation, if you like, the perturbation on top and the bottom, when they touch each other, they create droplets. The main point that I put here is to show you that those droplets have a certain size, which is basically the average drop is nearly twice the diameter of the undisturbed jet. This is a known property, and you can see here a jet of some liquid that create those droplets. Of course, when it becomes highly nonlinear, then it becomes more complicated. Anyway, the intention was not really to discuss this in detail, but just to talk about the fact that the liquid jet will create droplets. Now, spray combustion is very complicated because you could have a variety of things happening. You could have, first of all, the droplet vaporize. So you have fuel vapor everywhere here, but you also have droplets. You could have a cloud of droplet burning together. You can have individual droplet burning, as you can see here schematically, and you can have an overall flame that encompasses the whole thing. It's a diffusion flame that I show you. So this is just a schematic to show you how involved will be spray combustion. To describe this, you have to track the liquid, you have to track the gas, you have to track the surface of all the droplets, and it's a very complicated problem. There are different approaches in the literature, but that's not the intention that I had to discuss. All I wanted is to focus the attention on a droplet burning, on a single droplet burning. And so a single droplet, you have a fuel drop, it vaporizes, you have a diffusion flame that it established at some distance, and it's established where the fuel vapor meet the oxidizer, which diffuse towards the droplet. Discuss this in the absence of gravity, single component fuel, otherwise the condition in the droplet surface will be more complicated, and a quiescent atmosphere, in other words, no motion of the oxidizer. The first expression that I want to establish is, since the droplet shrinks as it evaporates, then there is a relation between the time rate of change of the mass of the droplet and the mass flow rate that leave the surface. And you can establish it here, and if you assume that the density of the gas is relatively small compared to the density of the liquid, which is typically 10 to the minus 2, 10 to the minus 3, of course, then the RS dt, the history of the droplet radius, is, if you like, rho g times v is the mass flux out of the droplet surface divided by the liquid density, okay? In fact, this condition was also established before. I did that in one of the first lectures where I showed you how you derive boundary condition across an interface, and I chose the droplet as being the example, and I exactly derived this from mass conservation, assuming again the same assumption that the otherwise you get this relation. So this assumption leads to what is known as quasi-steady approximation, which means that the mass flux, which I denoted here by m dot, which is leaving the surface, well, whatever happened in the gas phase, or the droplet rather, reduce or shrink at a much lower rate than what is going on outside. So you can describe the processes in the processes in the gas phase from essentially steady equation for a given mass flux. And then a posteriori, once you know the mass flux, which is rho GV, you can describe the history or the time change of the droplet. This is known as a quasi-steady approximation. If you want more mathematically precise statement is the following. If you assume that rho G over rho L is the small parameter, then in all the equations, say for the temperature and for the mass fraction and so on, you're going to have an epsilon. When you scale things properly, you will have an epsilon appearing in front of the time derivative. And so to leading order, this is small compared to the rest, and so the equations are effectively steady. Okay? The only one which is not is the equation here. So we can solve the problem, and here is what I have shown you early on in the notes. This is the jump relation. You get exactly the same relation, but you also get the condition at the boundary, at the interface, what is the proper boundary condition for the fuel and oxidizer. Since I discussed those in the past, I will just leave them with not further discussion. For the temperature, this jump gives you the following. We're going to assume that the temperature of, we're going to assume that, first let's describe this. So this is the difference between the heat conducted to the droplet and what is conducted inside the droplet. A plus and A minus are A is the radius. And the difference here, which comes from the difference in enthalpies, which appearing here in the more general equation, is the difference between the enthalpy of the gas minus that of the liquid, so it's related to the latent heat of vaporization. So out of this you can obtain an equation, but we're going to further simplify it by assuming that the heat conducted towards to heat up the droplet can be estimated from this relation, and then we will often neglect this or incorporate it into the latent heat of vaporization. So then people talk about, for example, you can see this in the book by William Serignano on droplet and spray. This is an effective latent heat of vaporization that takes into account whatever the heat is needed to heat up the droplet. But anyway, the idea, the point that I want to make is that we have a relatively simpler boundary condition to apply, which in fact we will simplify it further. And we want to solve the steady equation in spherical coordinates. And these are the equation you're familiar with, the reaction term. These are the condition at infinity and the condition at the boundary of this, at the surface of the droplet. We derive those. That's basically the convective plus diffusive flux of fuel is whatever is leaving the droplet. And the convective plus diffusive flux of there's zero because none is penetrating the droplet. And then this is the condition I just told you before. The total heat conducted towards the droplet, it's exactly the one needed to vaporize the liquid, which is the latent heat of vaporization. Now, in general, one needs one more relation which takes the form of the Clausius-Clapperon relation, which tells you that the partial pressure is a function of temperature or some relation between the local mass fraction of the fuel, if you like, and the temperature. But this is a bit complicated to deal, let's say, analytically, and so very often it's replaced by an assumption that the temperature is fixed, let's say the boiling temperature. The complication to do this requires a little more to do some relation numerically, but it's not of great importance. This is the problem, boundary condition very similar to before, and I will quickly just show the unity Lewis number results, simply because it's easy to describe. So first, pure vaporization, Dam-Color number equal to 0. I'm going to finish in less than 5 minutes. So Dam-Color number D equal to 0, no combustion. The profiles are what you see here, and the solution is expressed here. So the temperature increases all the way to T infinity, and there is a mixing of fuel and oxidizer. And since the problem also permit determining M is the mass flow rate in dimensionless form, okay? Which is in dimensional form was before the M dot here. All right? So mass. Okay, so eventually the idea is to write an expression for M, because that's unknown. Given a certain size of the droplet, what is the amount of, what is the flow rate of the vapor leaving the droplet? So for given condition, you obtain that it's this expression, and note that it depends on the difference between the temperature at infinity minus TB. So in order for the fuel, of course, to evaporate, then you need T infinity to be larger than TB, so that heat gets conducted to the droplet and permit vaporization. This factor here is often known as the transfer number, or sometimes the Spalding transfer number. It represents the impetus for transfer, which is the difference in the temperature between T infinity conducted towards the droplet, divided by the resistance to transfer, which is how much heat is needed for vaporization, or the latent heat. And clearly it should be positive, so T infinity is greater than TB. If we solve now the same problem, but for D going to infinity, namely full complete combustion, then of course the temperature rises to the adiabatic temperature or to the flame temperature, and then go down, and then the fuel and oxidizer are completely consumed at some reaction sheet. And so this is the flame temperature, location of the reaction sheet, and the mass flow rate, or burning rate, if you like. So the mass burning rate in dimensional form now, in addition to the previous factor, contain the total amount of heat, or the heat of combustion, which is this added here. So the transfer number now in the numerator include also the heat of combustion. So the impetus for transfer again is on top, and this is your new transfer number, and this is the position of the flame and the flame temperature. In short, you also obtain an S-curve. So you see that an S-type curve is really a representative of many diffusion flame problems, where the upper limit corresponds to the Berk-Schumann limit, the lower one, the lower branch, corresponds to the vaporization limit, and you can have either ignition or extinction when you increase the Dam-Color number above a certain value or decrease the Dam-Color number below a certain value. And in this case, the Dam-Color number, when you properly scale for the droplet, may correspond either to a change in the pressure level. So if you increase the pressure level, you can get auto-ignition, or if you decrease the pressure level, you can get extinction. Or it can be described in terms of A, the droplet radius. So when the droplet radius, it typically reduces. So when it reduces, come to a side where you can have a total extinction. Okay, so again, you have auto-ignition, auto-extinction. If you go back, and that's I will stop after this. If you go back and try to, then the mass flow rate is given by an expression like this when you put it back in terms of the original variable. Essentially, it's inversely proportional to the radius, okay? This is from the steady solution that we constructed. And now we want to put it in the equation that describes the history of the droplet. And when you do that, you have dRs dt is some constant divided by essentially Rs. The constant is written here. So you bring this Rs to the top. You have Rs dRs dt, which is a derivative of Rs square. You integrate, you get that the square of the radius essentially drop linearly. In the literature, it's usually expressed in terms of the diameter instead of the radius, and it's known as the d-square law. In other words, the radius, the diameter squared decrease linearly in time, and so when the diameter goes to 0, it gives you the total lifetime of the droplet. So the lifetime of the droplet is given by 1 over k, and k is an exact there's an exact relation for it, which is written here. And this is the lifetime. And experiments show that except for the early part, which is more associated with the early period after ignition, the droplet behave almost linearly like the theory predicted, and this is basically the d-square law, or the quasi-steady approximation. So I brought this. I could have discussed a few other things around here, but due to the time, I will stop. And next lecture, we'll talk about edge flames. So the last lecture this morning will be on edge flames, sometimes called triple flames. Not sure I like this term personally, and sometimes referred to as tribrachial, namely three branches flames. They were first observed. You see what I mean by three branches. There is a branch here, another branch here, and a third branch here, which I will describe in a little detail in a minute. They were first discussed by in the 65 by Phillips, where he was doing a model of a coal mine where methane tend to rise and establish at the roof of the mine. And then if somehow an ignition occurred, then a flame of this shape get established in that layer. But remember that the layer is not uniform. There's a gradient of methane, less at the bottom, more on top. And so that's one of the reasons for the creation of this structure. This is a picture taken later on, done in an experiment in a rectangular burner in a mixing layer. I added here just this for clarification. It's not part of the figure. There is a sort of a splitter plate with the fuel and oxidizer coming from different direction. And I don't remember the detail, but they had to do something on the side to create the proper stratification or whatever. But the key idea is this. If the Dam-Kohler number is infinite, then if this is the splitter plate and fuel is coming from here and oxidizer from here, okay, then let's say that's the tip of the plate. When a fuel particle just come upward, and an oxidizer come because they also diffuse. Then when the Dam-Color number is infinite, means the reaction is instantaneous, so the reaction time is, is very short. Then immediately as they get together, it burns, okay? And so you would expect the flame that get established from the tip up. But of course, the Dam-Color number is never infinite, and so it doesn't burn immediately as they meet. And so you can get a region here where they mix, and you have a premixed region in this region. And the premixed region, you're going to have a flame, okay? And since the flame is lean on this side and rich on this side, and since we know that the flame speed for lean or rich is lower than the flame speed at stoichiometry, then the flame would like to propagate here and here at a lower speed than this one, and that's why it curves, and it creates a sort of a curved premixed flame at this point. Then since on the left there is, and since on the left there is more fuel, then the excess of fuel will essentially leak through the premix branch that you have here, and there is excess oxidizer here that will leak through the premix branch that you have here. This one, of course, will be rich. This one will be lean. Then the excess will meet at a diffusion flame, and the diffusion flame extend upward. So the structure is a diffusion flame, two premix branches, and an edge, and that's why we call it an edge flame. Now, the edge must be sustained either by the fluid mechanics or by heat loss to the plate, and that's part of the discussion that we are going to see. So this is what the edge flame is, or the AAA. Now, it's relevant, of course, in lifted diffusion flames. Basically, I described it on the blackboard. You see here an observation. I added this burner just to show you where it's coming from. So you have a burner, and you have here an edge. Maybe it's not very clear because of the large picture, but if you focus on it, for example, here you see a more clearer edge. So you see an edge flame, and this is a schematic taken from some modeling of the diffusion flame. You see that the diffusion flame will be established here, and there will be an edge at the when you get closer to the burner. Edge flames are also relevant in, or highly relevant. So it's one application or importance is lifted diffusion flames. Now that's important in practice because very often you don't want the flame to be too close to the burner. It can heat up the material, cause corrosion, and so on. And so it's good to have it somewhat lifted. And so it's relevant in those studies. It's also relevant in turbulent combustion because what happened due to a high strain locally, it's like the top of the S curve that I showed you before. High strain cause a decrease in the Dam-Color number, and as a result, you may have extinction at some local place along the surface of that diffusion flame. And so here is, for example, holes shown from some DNS done by, in the 2004 by Carlos Pantano. And then when you have a hole, and you can see here also a hole in some other jet calculation. You see here the entire jet. This is a local picture. And when you have a hole, then you have an edge. And so that edge depends on the condition, because you have temperature fluctuation, and you may have, first of all, when you have a hole, the fuel and oxidizer, we're talking about a diffusion flame. So the sheet or the surface separate more or less fuel from oxidizer. I say more or less because there may not be purely fuel or purely oxidized. So when you have a hole in the region of the hole or through the hole, the fuel penetrate the oxide and they start mixing. So you have a premixed condition, which can get reignited if the temperature fluctuation are high enough, or if the strain rate is reduced, or whatever the conditions, the local conditions are. And so that flame can reignite as a premixed edge that I showed you earlier. And if it gets reignited, it closes the hole, right? So it repairs the diffusion flame, if you like. But under some condition, it could even get further and further extinguished. Now that you have an extinction, so the hole can even spread further. So the relevance of edge flame in turbulent combustion is important. This comes from simulation done by one of the lecturers here with Vervish. He's not here today. Sometimes he sits in the audience. So anyway, tell him that I show his picture. And so, edge flames are responsible for reignition and re-extinction. So, but edge flames are also of interest in premixed combustion. Remember we talked about the twin flames, right, in the counterflow. So this is described, at least mathematically, we looked at the two-dimensional problem, which means that the flame is a sheet in the third direction, not y, not z, in x. That goes all the way to infinity. But in reality, very far in the x direction, the temperature, very far, to some extent in the x direction, temperature can be cold or drop. And so clearly the flame on the top and the flame on the bottom would have to get connected, okay, and there is no flame behind, and that forms an edge. So that's exactly what I'm showing you here. It's cold, so it forms an edge. And this edge in a straining field was also attempted to be described experimentally, but experimentally what he had done to try to get the edge or to try to create the edge from the diffusion flame was to have the two burners slightly slanted. So you see, remember that the flow field has a constant strain rate. I called it epsilon or 2 epsilon in my previous note. So when the two burners are slightly standard, the epsilon decrease, and the epsilon decrease causes a change in the Damcolor number, and so can cause extinction. So it will be extinct here, and so it must form a sort of an edge in the extent, in some distance away. That's experimentally done by Paul Rani. So in this lecture, we're going to focus on edge flame in a mixing layer. So you have a mixing layer of fuel, oxidizer coming some stream, and you have an edge formed here, and I already explained why there should be some edge form in this region. Well, this is essentially a repeat of what I said on the blackboard. If the Damcolor number is infinite, you expect that the flame will be attached to the edge of the plate, but otherwise it will create a premixed region here and an edge form. This is a computation result. Those are reaction rate contour. So it shows you essentially where reaction is important, and therefore it shows you the shape of the edge flame. To really discuss the problem with a variety of property and condition, we are going to use, or we're going to adopt a constant density approximation. In other words, we're going to neglect the fact that the gas expansion have an effect on the edge. I will touch on that a little bit towards the end of the lecture. And so the problem that we have to discuss is, in fact, precisely is an infinite problem. X and Y goes from negative infinity to plus infinity. Now, there is a plate here, but since in principle, if the flow is coming, you may have backward diffusion, then you have really to integrate the solution sufficiently far from the plate down to all the way to infinity. And so even though we, not even though, we are adopting a constant density approximation, we have first of all to solve for the flow field, okay? And so we solve for the flow field. We use the, of course, we solve the Navier-Stokes equation. And then once we have the flow field, we prescribe the flow field and solve for the combustion field with two reactants, fuel and oxidizer, and that's the energy equation. The rest is standard as we have discussed this week. What we want to focus on, or want to do a parametric study to examine the different variation of the overall flow rate, what happens when you change it, how does it affect the edge. We are going to talk about stream of unequal velocities. In other words, the top and bottom velocities don't necessarily are equal. We're talking about preferential diffusion, different diffusion rate, mixture fraction, variation, not fraction. What I meant is mixture strength, so apologize. In other words, that parameter phi that I told you, or if you like, equivalence ratio. And thermodiffusive, thermophysical plate properties, I will maybe touch on that a little bit. There are, of course, studies in the literature that accounted for density variation, but they had to compromise on something, either compromise on the boundary condition, for example, forcing the boundary condition at x equal to, say, 0, if that's 0, so that in a way don't allow for backward diffusion, or consider a steady flow, an isothermal plate, or assuming very specific condition, a specific fuel, a specific condition. And there are also studies that have assumed a priori the shape of the flame, which of course is not the case in principle, because the shape depends on the flow and so on, but they looked at it. It always looks very parabolic in shape, so what if you assume it to be a parabola? But so it's interesting study because they illuminate on the problem. And so, I wanted to make that as a general comment. Now, the flow field in the wake of two unequal merging stream is usually discussed in the non-reactive case in the limit of large Reynolds number. And what you have, if this is the plate, you would have a boundary layer and a boundary layer here. If the velocity is different on top and bottom, then this one is u, and this is, say, alpha u. Alpha will be a coefficient between 0 and 1, right? Alpha equal to 1 is the same. Alpha equal to 0 means that there is a fuel stream, no oxidizer stream. The oxidizer come from the ambient, so it will be entrained into the flame in that case. So it's like, if you like, equivalent of, say, a jet of fuel in a quiescent mixture where the oxidizer, in a quiescent ambient, the oxidizer get entrained, or two stream of fuel and oxidizer, but not necessarily of the same velocity. Now, what is known is that again, in the non-reactive case, is that far away there is a wake, and that's the velocity profile in the wake. And in the near wake region, there is a well-known solution due to Goldstein, which the assumption is that it admits the boundary layer approximation, but it has the following form. It's a similarity solution. Similarity meaning that the problem is described of a single variable, which is y divided by x to the 1/3. And then the solution is a function f of eta that admit an ODE that can be solved. And then u is the axial velocity is f prime, and the vertical velocity is this combination, okay? And let me see what here are solutions for different alpha of the Goldstein similarity solution. So this is f prime, which is the axial velocity as a function, as a function of this eta. Remember that eta is practically, if you want, y, in other words, the vertical velocity or the vertical distance. And so, of course, it's symmetric when alpha is 1, and when alpha equal to 0, then it's, of course, 0 here, and then it's the axial speed, right? And then you have the vertical velocity. Vertical, I mean in the other direction, the y direction. This is the axial speed. This is effectively the problem with Goldstein solution, that it has a singularity at x equal to 0. You see it from here very vividly. When x goes to 0, v goes to infinity. So that solution cannot extend all the way to the splitter plate, which means that there must be a non-uniformity in this region, and the non-uniformity has to be described by the full Navier-Stokes equation, okay? So this is the picture, the fluid mechanic picture of this flow. You have the near wake region, or the Goldstein solution, and you have a region here which in terms of the Reynolds number, the Navier-Stokes lengths divided by the length of the boundary layer, it's Reynolds number to the -12. Remember that the boundary layer in terms of the global flow is also Reynolds number to -12, so there is a more complicated expression if you want to describe in terms of say the Reynolds number based on the plate lengths and so on. Okay, so the idea is that we want to solve the problem in this vicinity because that's where perhaps the edge gets established in the Navier-Stokes region. Although sometimes it could be lifted sufficiently far that it gets established here. So actually what I will be showing you is solution of the edge in this region as well as in the further wake region. The difference is that in this region I know already the velocity field, so all I have to do is just to plug that in the equation for the temperature and mass fraction, whereas in this region I have first to solve the Navier-Stokes equation, which I will show you next. But before I do that, let me just indicate that even though I'm solving the problem in this region, which is a Navier-Stokes region, I have to solve the equation sufficiently far to the left because, again, I cannot prescribe condition at the tip of the plate. I can only know that if I go sufficiently far, I have essentially the boundary layer solution as my solution. And when I go sufficiently far to the right, in other words, boundary condition at infinity should match with this flow. In other words, I cannot just prescribe say, simple boundary condition to my liking. It has to fit this flow. And so that makes the problem a little more interesting. Now, since this region is small, the boundary condition very far to the left, namely as x goes to negative infinity, is sufficient to describe the slope of this Blasius type solution, boundary layer solution. So this is the mathematical problem in the Navier-Stokes region. We have, if you like, different strains on top and bottom, minus because it's below the line, y negative, alpha is between 0 and 1, and the solution far away, as I said, must satisfy this. So this is the equation. Luckily, if you scale things correctly, correctly meaning with A, which is, what is A? A is a unit speed, or A is the slope here in dimensional form. It turned out that the Navier-Stokes equation become with no parameter. In other words, you scale basically whatever the Reynolds number that you will normally appear here, it's scaled in the equation. And so you have to solve this once and for all for alpha, for different alpha, okay? And so the solution is shown here. For alpha equal to 1, you expect a symmetric flow. So the two stream coming from the two direction start merging and they accelerate in that region, okay, as they move beyond the tip. If alpha is not 0, then of course the gradients are different, and this is the limit where, well, it's close to solve the problem for alpha equal to 0. Turned out to be very difficult numerically, so of course we stopped at a small alpha that is representative of what would happen when alpha is near 0. And so what you see is that the flow here is of the fuel, and the oxidizer is entrained from the ambient into the mixing layer, okay? So this is the fluid mechanic solution, and we know it, so now we can substitute it in the V. Of course, the whole problem is discussed now numerically, and solve this equation. The equation is the temperature. Theta is expressed as the temperature minus T naught. T naught is the temperature of the ambient mixture, assumed to be the same, and T naught is therefore the temperature of the plate. For now, we are assuming that the temperature of the plate is constant and is T naught. And so T minus T naught divided by T stoichiometry minus T naught. I don't know yet what T stoichiometry is, but it will be obtained as part of the solution. This is what theta is, and so it gives you this equation. Then you have an equation for YF. YO is different Lewis number. The mixture strength phi, defined exactly like in the previous lecture. And so these are the important parameters that we want to focus on: Lewis number of fuel, Lewis number of oxidizer, mixture strength, and Dam-Kohler number. The Dam-Kohler number is controlled by the flow rate through this A, okay, which is the strain rate of the incoming flow. And even though we are addressing the problem numerically, it turned out that from the knowledge of some of the asymptotic study we did before, it's convenient to define, to rewrite the exponential by multiplying the rate by e to the positive e over RTS, e to the minus e over RTS, simply because then you get a more balanced number. You don't get numbers which are very large or very small in the reaction term, and so it helps in some of the numerical discussion. Anyway, one thing which is quite clear, when alpha equal to 1, we have seen that before, the flow field is symmetric. If Lewis number of the fuel and oxidizer is 1 and phi equal to 1, you can easily see that the problem is symmetric. Symmetric meaning that I can exchange YF with YO, and or you get the same thing as YF as YO, same equation, and so you expect the edge to be symmetric. It's quite clear from the equation. So any asymmetry will result either from the flow field, from different diffusion rates, from different mixture strength condition, namely if the system is more rich or lean. But if it's at stoichiometry, then and the other things are 1, then it will be symmetric with respect to the axis. Oh, here is a picture of a symmetric edge. Lewis number 1, Lewis number 1. For some reason, the color are a little different than what I remember them. But anyway, phi equal to 1, alpha equal to 1. You see, here is the edge. Those are reaction rate contour. So yellow means a higher rate. That's where the diffusion flame is. So the temperature or the reaction is quite significant here. You see also the shape of the edge. And this is the temperature field that show variation in temperature across the field. And as we expected, everything is symmetric. And this is the fuel concentration on top, oxidizer concentration at bottom. So you see the fuel, there is more fuel here, there is none here, and then of course there's a gradient towards the diffusion flame. The opposite is true with the oxidizer. Non-symmetric edges. So here is the picture with alpha equal to 1. In other words, the velocity field is symmetric, but the Lewis number, I just want to, this example, Lewis number of the fuel and oxidizer was assumed to be the same, okay? Different figures will correspond to different things, so I have to remember what it is. And phi is equal to 1. So the only thing that, unequal, I don't know what unequal stream strain rate is because alpha, this one is 0.1. Okay, so first equal stream strain rate, alpha equal to 1. The two Lewis numbers are chosen to be the same, equal to 0.8. And so you see that the edge is a little bit off the symmetry line. But when alpha is close to 0.1, so that the oxidizer is entrained into the flame, and the Lewis number is 0.8, we see that, again, there is the flame lean more towards the oxidizer. The reason is because the Lewis number, the reason is because of the flow in this case. It's not the Lewis number are the same, so the fuel and oxidizers diffuse at the same rate, but the flow here is stronger than the flow here, and so it tends to, the flame tends to be on the below the symmetry line. These are temperature and concentration of the fuel and oxidizer for the same condition that I described. This comment was an important one that I want to emphasize. Note that the branch of the fuel rich, which is the top one, it's a little longer than the branch of the fuel lean. So sometimes you will see that those two branches are not necessarily equal. In fact, sometimes one of them can totally disappear and you see only one of them, okay? So it depends. Now, the extent that it's longer, it's maybe a little misleading because it depends on the scaling of x that the figure is displayed. So don't read too much into the relative length. This is a non-symmetric edge flame due to preferential diffusion, unequal Lewis numbers. So you have the Lewis number of the fuel and Lewis number of the oxidizer are different. The oxidizer is taken to be 1. The Lewis number of the fuel is taken to be 1.8. So Lewis number is the thermal diffusivity divided by the fuel diffusivity. Being larger than 1 means that the fuel diffusivity is low, and so the fuel diffuses at a slower rate than the oxidizer, and so that caused the flame to be more on the fuel side, but not very much, very slightly. You see the edge is above the center line. But in this case, when Lewis number is less than, significantly less than 1, you expect the flame to be on the other side, because fuel diffuses at a faster rate than oxidizer, and indeed the edge is below the center line. So the edge and the entire flame lean towards either the fuel or the oxidizer side, depending on their mobility, okay? So the mobility depends very much where the flame is located. This is, again, non-symmetric edge due to preferential view. So it's just a colored picture of something similar to what I have shown before. This is for Lewis number of the fuel 1.8, so it's very much more like the figure that I have shown you earlier on the left. Okay, and I don't know why it was repeated. Anyway, so this is a non-symmetric edge due to the fact that the initial mixture the initial mixture strength, the mixture strength is quite large, phi equal. Remember, phi large means a rich system. So rich system, there is more fuel, and so the mixture is rich in fuel. Note what happened is that the edge has a hook-like, it looks like more like a hook. In other words, this branch here is missing, with essentially a lean branch only extending all the way to the stoichiometric surface, okay? Now, where does the diffusion flame or the edge get located? Well, we expect that the diffusion flame is located more or less along the stoichiometric surface, because in the limit when the Dam-Color number is very large, or in the Berk-Schumann limit, then the stoichiometric surface determines location of the flame sheet. And even if the Dam-Color number is not extremely large, you expect it to be in that vicinity. And so indeed, if the mixture fraction is Z stoichiometry can be calculated. That's the location where YF and YO is equal to 0. And Z stoichiometry in the case considered here is 1/2. And so this is the stoichiometric surface, or this is the stoichiometric. So what happened when you increase the flow rate, the edge move further away from the edge of the splitter plate, but it seems to be always located in the near, such that the diffusion flame extend along the stoichiometric surface. And for Lewis number 0.8, it lies all the time below the symmetric line, and this is phi equal to 1, alpha equal to 0.1, same condition, but here the Lewis number is different, and so it tends to move towards the center. Diffusion flame lies practically along the stoichiometric surface, which is half, with its edge moving away from the splitter plate when you increase the flow rate or decrease the Dam-Color number. This is an important piece of information. What we've done, we've taken a long X. This is a non-unity Lewis number. So what we have done, we've taken the temperature profile along the center line where the diffusion flame is, with trying to do different calculation, but with different Dam-Color number, because remember, when the Dam-Color number change, the location of the edge change. But we did different calculation to bring the edge in almost the same location for all the Lewis number considered, so that they are all located at approximately the same location. So it corresponds to different damn color number, but the edge look. And the reason for this was just to compare what will be the temperature profile along the, say, the center line, if you want, or along the location where the flame is, from the edge of the splitter plate down. So, of course, near the splitter plate, theta equal to 0. The temperature is T0. And then this is a premixed flame, so you expect like a premixed flame, a preheat region, right? Now, if the Lewis number is equal to 1, the flame temperature is the adiabatic temperature, which is 1, okay? Which is the purple curve, which is also the temperature of the diffusion flame. But when the Lewis number is not 1, remember in the previous lecture, the diffusion flame, the temperature, the stoichiometric temperature is either superadiabatic or subadiabatic, depending on the Lewis number. It can be above or below. So it will be above when the Lewis number is less than 1 and below when the Lewis number is bigger than 1. And so what you see is that the edge temperature is dictated by the diffusion flame and not by the premixed flame. So the diffusion flame dictates the temperature of the edge. In other words, heat is being conducted towards the edge and raise its temperature. So this is, again, unlike a planar premixed flame, where the adiabatic temperature for all Lewis number will be the adiabatic flame temperature. The stoichiometric temperature of a diffusion flame is super adiabatic, depending on the Lewis number. And the edge is determined by that. Now the standoff distance. Here is 2 cases that I described, and let me discuss them first. So it seems like there is a difference between the behavior of the location of the edge as a function of the damn color number. Remember, damn color number increase, the flow rate is opposite or inversely to the flow rate. So, sorry, the flow rate is in this direction. Now, x, the reason for a bar is just here scaled on the diffusion length. So scale on the diffusion length tell me that when it's very close to 0, you are very close to the plate, right? It's a very small distance from the plate. Okay, what you see the difference is this. The low Lewis number, which is low, I call the Lewis number with 1, low compared to, relative to. As you increase the flow rate, the flame gets closer and closer to the plate. Doesn't change very much, but it gets closer and closer to the plate. And then there is a turning point here, which means that if you increase the flow rate beyond that point, there is no solution, so this point would correspond to extinction. So when for low Lewis number, the edge will practically be very close to the splitter plate, maybe practically attached, you can say. Because again, XC is like of the distance of the flame thickness, and the edge is blown off when the flow rate exceed a critical value de-extinction. Just for the purpose of discussion, these curves were created in the Navier-Stokes region, and this dash dotted with in the wake region. The same thing in this curve. This is a wake region. The point here is that the solution Navier-Stokes and the solution in the edge just blend quite nicely into each other. There's a consistency here. Okay, now what happens when Lewis number is larger than 1? Forget this section. I'll talk about it later. So when you increase the flow rate, you keep on, the flame gets closer and closer to the edge. You keep on increasing. Now it goes further and further away from the edge. There is no turning point. Right? So what it means, it's like the flame in a porous plug. It gets close to the edge, there's a minimal standoff distance, and then it can go away. Well, here it can go away, maybe there it cannot because it was flat. And so the flame gets lifted further and further up, okay? So in low Lewis number, you have extinction. High Lewis number, the flame get lifted and get lifted sufficiently far. This is just to show you that that's true for different Lewis number, and it seems like the transition from one to the other seem to be somewhere around 1.2 or so. Nobody said that 1 is the magic number. Sometimes it's a little off 1. And also this corresponds exactly to the observation on Chung and Lee. For light fuel like methane, ethane, the flame remain attached to the rim of the injector, is blown off when the flow rate exceeds critical value. And for heavier fuel like propane or butane, the flame lift off and stabilize at significantly large distance from the rim when increasing the flow rate. When I first saw the experiment of Chung, he did a very nice one in front of the audience. Unfortunately, I cannot do that. He had 2 lighters, exactly cigarette lighters. On one of them, he created a very nice tip so that you know, you have a good, well, you have a jet. And when and I think he had a propane or butane, I'm not sure, probably propane. And when he lighted and increased the flow rate by pushing your button, the flame lifted practically something like this. And it was established here on top. So it was quite impressive to see. I'm sure that some other people have done this in the lab. So this is this. Now, we want to talk about what is this region here. So this region corresponds to an instability. In other words, we took the existing solution that we constructed numerically, and we added a small perturbation to it. And we saw that the flame is not steady, but it's not blown off or extinguished. And what happened is what you will see in the next figures for different points here along that curve. So this is just to clarify, it's a segment, it's this segment in this part. This, by the way, is stable, and this is stable, meaning that the edge is sustained steadily. The edge sits there under this flow, doesn't move. So what happened in this region? Well, when you are in A or in this point, I, then you do a small perturbation. After some time, the solution tends to a constant, which is the edge position here and here. I told you those are stable. When you go to points in between, you see that there is a sustained oscillation in the top. In B is with 1 frequency, in D with multi-frequencies, and then the amplitude keep on increasing. Eventually, it's decreased and it becomes stable again. So it's stable, start to create oscillation with different frequency, and get stable again. So in other words, there are 2 modes of stabilization. In one mode, the edge is just sitting there. In the other mode, the edge is oscillating, but it sits there, so it doesn't get blown off, unlike the low Lewis number where the flame gets blown off. Here are just movies that show this oscillation. This is the single frequency, and this is the multiple frequency of the oscillation. Okay. We also discussed here the edge speed. In other words, we can determine what is the speed that the edge would want to propagate into the mixture. And it seems like it's related to the gradient of the, Well, it's essentially the local dissipation rate that I have discussed or briefly mentioned in the previous lecture. So, but the local one, the local value at this point, and that defines what we refer to as an effective Dam-Kohler number. And the relevance of the effective Dam-Kohler number show that, you know, all the curves for different Lewis numbers seems to tend to that same value, or to the same, the same value when the flow rate, you know, is relatively small. So even though the edge flames in this limit stabilize a scattered position, then the curves of different Lewis number collapse to a single curve. The effect of thermal expansion. There are two effects of thermal expansion which are a little different. One is on the edge itself, which is a premixed, essentially, flame, and another one on the diffusion flame. Both of them we sort of discussed in previous lectures. So if you have a constant density flow, then first of all, the streamlines, this is the two streams are equal, and so you see they are symmetric. In this case, the edge is leaning towards the oxidizer because it's a rich system. That's the isotherm, or the temperature field. If the density ratio is, it's not a constant density, the density ratio about 5, it's about realistic values, then what you see, first of all, is the streamline tend to get deflected by the premixed flame in the same way that we seen when we discussed the hydrodynamic model yesterday. But there is also an effect due to the lateral deflection due to the diffusion flame. Remember when we did the counterflow, even though I was quick because I didn't have time, I show you that there is a displacement of the flow. Well, the displacement in this case is in this direction because that's where the diffusion flame is. So you have a displacement in this way due to the diffusion flame. So that's basically what it does. And the last couple of slides are related to the example that the plate now is assumed to be a conducting plate. So it's no longer, we want to see what is the effect of the conduction of heat along the plate on the edge. And so the plate is not necessarily maintained at a constant temperature. And so it's easy to derive an equation for the temperature along the plate, which we call theta wall or theta W, when h is small. In other words, you take the limit h very small. So what you get is essentially like a heat equation along the plate in the x direction, that vary in time, of course, with a jump in the temperature from the top to the bottom, okay? So that affects this equation. That's effective. This term comes to the fact that the plate has also some thickness, and when you take the limit, when h goes to 0, it just reduces to this equation. And so there is an analysis of different kind of plates that were considered. But anyway, I will be brief about this, but just want to say that the heat gets conducted along the plate, and the extent that it gets conducted depends on the conditions. And so some heat get, now the hot plate conducts to the cold fuel and the cold oxidizer, and so there is what may be often referred to as an excess enthalpy flame. In other words, you add from the hot, you add the heat which comes from the flame, from the combustion, through the plate into the unburned mixture. You heat up the mixture, so it affects the flame. And so this is what you see. I'm not going to discuss all these details, but this is what you see in a cold plate, but in plates where there is an effect on the plate are these where, you know, the extent of heat that get into the plate and affect the transfer. That's what I just was describing in words before, and just wanted to quickly show that you can see edge flame also in different configuration. One of them that in a corner, so the fuel and oxidizer come from one vertically, one horizontally, and the diffusion flame is established. In this case, Lewis number 1, diffusivity were equal, and so on. And so you get the flame established, a diffusion flame established here with a clear edge at this location. And there are displacement due to Lewis number, different diffusivity, similar to what we have seen before here as well, and dependence on mixture strengths. Before I end, I want just a little anecdote, maybe. See if I have it. So strolling into some of the street in Paris, which is one of favorite cities that I like to visit, I saw a nice plaque. It was a store that keeps on all kind of things that were collected probably somewhere. My guess it was collected from some industrial or experimental lab, and this is what it says. So there was no author, doesn't know anything. Those that know French, just ignore what I said. I'll say it in English in a minute. So I'm translating what it says. So it says the theory, when we understand everything, but nothing works. That's what theory is. And the practice, I mean application, everything works, but we don't know why. And then here, I don't know what here is. I'm assuming that it's where this lab was taken. It says, we have succeeded in both. Nothing works. We don't know why. Thank you very much. See you tomorrow.